I'm Andrew Waterman. I'm Sci5's chief engineer, and I'm one of the original instigators of the RISC-V project. So it's great to be here in Catalonia to talk to you about the work that we've been doing for a number of years now. So today I'm going to talk about the base ISAs and their standard extensions. And I think one of the greatest things about RISC-V is that we can do this whole thing in a half-hour-long tutorial. Rick and I failed to compare notes before putting our slides together, and it turns out that we actually have nearly identical introductions. So the fact that Rick was a few minutes over time ends up working out fairly well. So I'm just going to add one little anecdote to this story here. So back in 2010, a couple of research projects we were working on at Berkeley were winding down. We were building a mini-core FPGA-based simulator based around the Spark V8 ISA and a high-performance vector accelerator based upon a lightly modified MIPS, basically like MIPS 32 minus branch delay slots and some other stuff like that. And since it was time to start a new batch of projects, we wanted to unify around a single ISA, and so, you know, one of the main reasons that you want to unify behind a single interface is for the software. You know, as important as it is to have a vibrant hardware design ecosystem, the reason that we care about ISAs is because you want to be able to run the same software across a bunch of different hardware platforms. And so the natural thing to do was to look at the most popular ISAs in use at the time, which were x86 and ARM. So the first thing you do when you think about implementing an ISA is you go open up the manual and read it. So I want to see a show of hands. How many people here know what the AAA instruction in x86 does? All right, that's I count two. So this is the very first instruction in the manual. So, the semantics of it aren't too important, except for how irrelevant they are. So what this instruction does is it performs, binary coded decimal addition, which, it turns out computers don't really do a whole lot of these days. And you can see the semantics up here. It's fairly complicated, but certainly not insurmountable. The thing about it that really doesn't make any sense at all is that this esoteric operation that no one really cares about was given a 1-byte opcode. So in the entire space of the x86 code space, obviously there are only 256 of those available, and several of them were given to this family of BCD operations, and several more to other things that happen almost never. So, it seems like there was not really a whole lot of forethought that went into designing the ISA with code density in mind. So in addition to being complicated, it's not even complicated for good technical reasons. Historical, yes, that's a good euphemism. Yeah. So if x86 is impossible to implement, or at least undesirable to implement, I guess we would say that ARM is very close. It's not impossible, but it's virtually impossible. So this is an example of an instruction that at least actually is used and is useful in ARM v7. So this is load multiple increment address. And the EQ there indicates that it is conditional. So what this does is it loads 6 values from memory, loads 5 values from memory, writes 6 registers, including the PC, which is, if you're familiar with ARMv7, is one of the 16 general purpose registers, which is actually an oxymoron. They're obviously not general purpose. And worse yet, it is the EQ, as I said, indicates that it's conditional. So it's loading all these registers from memory, loading all these values from memory, writing all these registers, and conditionally updating the PC. Now, the one other hitch about this thing that's kind of funny is that if you're an ARMv7 expert, you know that the LSB of the program counter indicates whether you're in thumb mode. So in addition to doing all this stuff, it's also conditionally changing the instruction set. So, you look at this and you're like, why would I want to implement this if my goal is to, so as I was saying, we were looking at these ISAs for the purposes of building processors around which we could do our, computer architecture research. We don't want all this baggage. It's not particularly helpful. So, despite all that, at least this instruction gets used, unlike AAA. So, as Rick said, we grossly underestimated the task of designing the RISC-V ISA. It took us about 4 years instead of about a semester. It's not like we were all just crammed up in some windowless conference room, writing the spec the whole time. We did build about 10 chips along the way, and the ISA evolved from our experience doing so. And if you go take a look at one of the RISC-V specs from 2010, I think that they're probably still available on some of those Berkeley course web pages. You can see the similarities between the current design and the old designs, but they really are quite a bit different. So for the rest of the talk, I'm just going to dive into the design of the RV32I base ISA, talk briefly about the other base ISAs, and then talk about 5 of the most popular standard extensions. So one way of thinking about an ISA is its architectural state and instructions that operate on that architectural state. So I think the easiest way to think about how RISC-V works is to first define what the architectural state is. And for RV32I, we're only talking about user level stuff here, no privileged architecture. But for the RV32I user ISA, all of the state is here on this slide. There's 31 general purpose registers, X1 through X31. The X0 register is hardwired to 0, as is the case for many RISC ISAs. And there's the program counter. So these are all 32-bit registers, so there is a grand total of 1 kilobit of architectural state in RV32I. There are 6 base instruction formats. It's really 4 instruction formats and then 2 others that differ in how their immediates are encoded. So there are some interesting features about this encoding design here. So you'll see I colored in red, green, and blue the register specifiers in this instruction encoding. So RD, where you write, which is what you use to write the results of an instruction to a register, is if it's present, it's always in the same place. Likewise, RS1 and RS2, if they're in the instruction encoding, they're always in the same place. So this helps reduce delay in implementations. So for RS1 and RS2, you can get the register read going before you've actually even decoded the instruction, and it reduces a little bit of muxing in the control path to have RD in the same place as well. And that starts to matter more if you're building superscalar and out-of-order implementations. Some other interesting aspects of this encoding is, it's kind of hard to tell from this picture, but if you squint, you can see that the most significant bit of the immediate is always furthest to the left. So that means that for the other base ISAs like RV64 and RV128, you can start the side extension of the immediate without having decoded the instruction yet. So that's the most critical operation on an immediate. So that helps things a little bit there too. But the high order bit here, though, is that the instruction encoding is simple and very regular. So how can you operate on that architectural state? So RV32I defines some arithmetic operations. There's 10 of them. There's the usual suspects that you see when you just look at a C program, like the C operators show up here. Addition, subtraction, logical operations, the 3 shifts, left, right, and right arithmetic. And a couple that are inherited from the MIPS ISA design, which are a bit more esoteric, which are setting a register with a Boolean value based upon the result of a comparison. So you can set a register if RS1 is less than RS2, either treating those registers as signed 2's complement numbers or as unsigned integers. And these arithmetic operations use the R-type instruction format, so they read RS1 and RS2, compute whatever operator on those two register values, and then write the result back to RD. So a large fraction of arithmetic operations have at least one operand a constant. Well, I guess if they had all operands a constant, the compiler would have propagated it out for you. So let's say 1. To take advantage of that property, we also provide immediate variants of all those arithmetic operations, with the exception of subtract, because if you have add immediate, you don't really need subtract immediate. So there's 9 of these guys. They use the I-type format. What they do is they read the register RS1, add it to the immediate, or do whatever operation between that and the immediate, and write the result back to RD. The immediates are always sign extended, even when the operation is logically doing something that's unsigned, and that's just to simplify the implementation. We studied a bunch of programs when we were working through this design and found that actually not having some unsigned immediates slightly improved code density for the ISA, so doing the simpler thing at a performance win is kind of a no-brainer. It is perhaps a bit mind-twisting that you're sign extending an immediate that you're going to be using in a set less than unsigned instruction, but so be it. So one other feature about the I-type encoding here is you'll see that the immediates here are 12 bits wide. So in some RISC ISAs, MIPS being a notable example, the immediates were 16 bits, and that chews up a tremendous amount of encoding space. So using only 12-bit immediates here gives us a lot more expansibility in the opcode space, and also enables an optimization where we can compress code, which I'll talk about later on. So this is all of the RISC-V, well, all of the RV32I arithmetic instructions on one page. So not a whole lot going on here. I don't intend for you to stare at this and get anything out of it. The point is that it's pretty simple. And you can see the regularity in the encoding here. So you also need to get stuff into and out of these registers to be able to do anything interesting. So RV32I defines some loads and some stores. There's 5 load instructions, 3 for each of the logarithmically or exponentially increasing data type sizes between 8 bits and 32 bits. So there's load byte, load half word, and load word. The ones that are smaller than 32 bits sign extend their results. So you always write the register you always write the entire register. There's no partial register updates here, even when you're operating in quantities that are smaller than the size of a register. There's also unsigned variants of the byte and half word loads. So when you're operating on unsigned data types, you can avoid having extra operations after loading the thing in. So the loads all use the I-type format, just like the arithmetic instructions I mentioned before. Same instruction format. What they do is they add RS1 to the immediate to produce an effective address. Then they go dereference memory at that address and do whatever sign or zero extension is necessary, and then write RD. And that's all of the load instructions in RV32I right there. So the stores are fairly analogous. Same thing, you add RS1 to the immediate to generate an effective address. Then you take the least significant bits of the register if you're doing a subword store. So it's all write justified in the register, then store that thing to memory. So this is where you might see this immediate shuffling showing up. You see that in bits 11 through 7 of the instruction is where the low order bits of the immediate were. If you go back to the loads, you see that bits 4 down to 0 of the immediate were up in bits 24 through 20. Now, the reason we do this is because that way we can keep the RS2 register specifier in the same place, again, simplifying the data path design. The cost here, of course, is that when you generate the immediates, you have to do some shuffling, and when you're trying to present this in like an undergrad textbook, it kind of confuses the hell out of people, but it's a worthwhile optimization. So on the topic of loads and stores, sometimes the address that you're trying to access is not magically granted to you in a register. You need to access global variables, and so we provide a couple instructions to help with that. So these 2 U-type instructions, LUI and OWPC, are here to provide global variable addressing and also for some other operations. So you see that they have a 20-bit wide immediate. And as you've seen from the other instructions, they have a 12-bit immediate. It's not coincidental these two sum to 32, so you can use LUI in conjunction with one of the I-type instructions to form a complete 32-bit address. So this little code snippet here is how you load an arbitrary 32-bit address. You access memory at an arbitrary 32-bit address and load that quantity into a register. So LUI is also used for just synthesizing constants. If you just want to generate A, B, C, D, E, F, G, 8, well, that's past F, A, B, C, D, E, F, 1, 2 in a register, then you use a LUI to load the upper 20 bits of that and add immediate instruction to add in the lower 12. So OWPC is a little bit of an oddball here. It's doing something similar to LUI. It has a 20-bit immediate, but then it adds that to the program counter. And then writes that into a register. So you use this as one part of a PC relative addressing scheme. So why do you want to do this? Well, the main answer is that if you have dynamically linked programs, those programs can be loaded to memory at some place that is not known until load time rather than at link time. And so you want to be able to access variables relative to the current location of the program counter. So this enables a 2-instruction sequence for accessing anything that's within 32 bits of the PC. Branches are important because they're the things that distinguish computers from calculators. So naturally, RV32I has a few of those. You could always get away with a very simple thing with just say branch against 0 or branch of negative or something like that. But it turns out if statements happen a lot in code, so we provide a bunch of these branches. So they use the B-type format, which is very similar to the S-type format that stores use. The only difference here is that the immediates are yet swizzled again. And the reason why is because it doesn't really make sense to branch to odd-numbered addresses because instructions are always, well, in the base ISA, always at least they're always exactly 4 bytes wide. And so you don't need to encode that 0 bit. So the branches have twice the displacement here. They can address up to plus or minus 4K instead of up to plus or minus 2K, as would be the case if you didn't do this. Now, why is it plus or minus 2, or why is it times 2 rather than times 4? That's because RISC-V ISA extensions don't necessarily have this constraint that all instructions are 32 bits. So one instruction I'll talk about later has 16-bit wide instructions, so you need this ability to branch to arbitrary 16-bit offsets. And other ISA extensions, like say custom extensions or things that are yet to be defined, may well define 48, 64, 80-bit long instructions. So we want to be able to support branching to any 2-byte offset there. So the way these branches work is they read registers RS1 and RS2, and they perform some comparison on them. And then if that comparison is true, it increments the PC by the immediate. Otherwise, it just falls through to the next instruction. So the comparison options you have here are equality and inequality, and magnitude comparisons, like less than, greater than, or equal to, and the unsigned variance of the same. So somewhat surprisingly, this is not an especially common feature of other ISAs that you can perform a magnitude comparison and branch in a single instruction. In x86, for example, you first have to set the condition codes and then do a jump. In ARM v8, they have some of these operations, but not all of them. Like you can branch against 0, but you can't do a full less than comparison between 2 registers. This actually it turns out to have a pretty significant impact on code size. So in addition to conditional branches, we also provide some unconditional ones, 2 of them to be precise. There's the jump and link instruction, which has a 20-bit offset, so you can jump within a megabyte of the current PC in either direction. It also sets RD with the value of the instruction after the JAL. So you use this to implement function calls. You need to, the function you're calling needs to know where to return to. So in one step, this writes a register indicating where you should return to and performs the jump. If you just set RD to X0, the 0 register is hardwired to 0, so you just discard the link address, and that turns it into just a simple direct jump instruction. There's also this jump and link register instruction, which is very versatile. It's used for returning from functions. So if you just set RS1 to the link register, which by convention is X1, then you'll jump back there. So that's how you get back from a function. You can also use it to perform indirect calls by setting RS1 to the address of the thing you want to call and setting RD to the link register X1. And it's also used for table jumps, like say switch statements in C programs. So one thing to know about JAL-R is that it's also the part of an idiom that we use for doing function calls to arbitrarily far away. So it would be nice if all programs fit in a megabyte, but they don't. So what GCC actually does, I guess, well, any RISC-V compiler that knows it could be targeting a code space of more than a meg, what it actually does is emits an OWEPC instruction followed by a JAL-R. So if you recall, OWEPC is used to generate a PC relative address and add a 20-bit upper immediate to it. JAL has this 12-bit immediate, just like a load instruction does. And so between the two, you can jump arbitrarily far away in a 32-bit address space. Now, obviously, it wouldn't be great if all function calls took 8 bytes to express, and so we use this technique called linker relaxation to turn the OWEPC JAL-R pair into a JAL opportunistically. So if you ever go, like, say, objdump a RISC-V object file, you'll see these OWEPC JAL-R pairs all over the place, but then if you link the program, you should just see JAL instructions. So the linker is performing this optimization. At admittedly great complexity, but it's a worthwhile code savings. So we're actually almost done with the RV32i base ISA. So there's a few instructions I don't want to talk about in this talk, but here they are for the sake of transparency. This really is everything. So there's the fence instruction, which provides memory ordering. So I will just briefly say that RISC-V has a relaxed but not too relaxed memory model. The fence instruction is there to restore greater ordering. And if you're interested in this, Dan Lustig is giving a talk which will probably tell you more than you thought you wanted to know about this subject later this afternoon. So you should listen to that. There's a fence.i instruction, which is used to implement self-modifying code. So by default in RISC-V, if you do a store to some address and then jump to that address, it's not guaranteed that the processor will fetch the thing that was stored. The fence.i instruction is there to synchronize between the data stream and the instruction stream so that you will fetch the right thing. There's eCall and eBreak to interact with the OS and the debugger. Use eCall to do a system call and eBreak to invoke the debugger. And then there's a bunch of these CSR whatever instructions, which are used to access what we call control and status registers. These are usually things that are part of the privileged ISA, say like the interrupt enable bits or whatever. They're also used to access things like the floating point status register in user mode. So if you're interested in what these things are for, Alan Baum is giving a talk later this afternoon about the privileged architecture, and he too will tell you more than you might think you wanted to know about that subject. So that was all RV32I. RISC-V is actually 4 base ISAs, not 1. They're all very similar to each other, but they are different. So there's a variant of RV32I called RV32E. That E stands for embedded, and what it does is it rips out half the integer registers, so you only have x1 through x15. And the reason you would do this is for very low-end implementations, and especially those that are implementing their reg file just using synthesized flops or something, the reg file is the dominant cost, or at least a dominant cost of the implementation. So this can reduce the cost significantly. It gets rid of 512 bits of architectural state. So there are actually non-low-end implementations where this might be interesting too. So for very deeply multi-threaded machines, for example, where the register file is also dominant but for different reasons, this is something you might use. So other than that, it's the same thing as RV32I. RV64I, on the other hand, expands the integer registers to become 64 bits wide to support 64-bit addressing. So this is the target of systems that want to have more than a few gigabytes of RAM or want large I/O spaces. Aside from expanding the integer registers, it's very similar to RV32I. All those arithmetic instructions I talked about before, now they operate on the whole register width, so like add immediate increments the entire 64-bit value. We have a few more loads and stores because we need to be able to load or store entire 64-bit values, and this LWU instruction is there because sometimes you want to zero extend 32-bit quantities. That's for things like unsigned integers. There's also a handful of new instructions. Unfortunately, in C programs, the 32-bit integer data types are ubiquitous. Sometimes this is for good reason, but more often it's just because it's bad code. You know, people are using unsigned int where they should be using size t and stuff like that. But in order to maintain decent performance on C programs, and I guess any programming language that has ubiquitous 32-bit types, we add a bunch of instructions that only operate on the lower 32 bits of the registers and then produce a sign extended result, write the whole 64-bit thing back to the register. So this is how you implement all these, like add, shifts, and so forth on int32 types in RV64. So finally, there's this RV128i down here. Now, we kind of defined this initially as this tongue-in-cheek thing. But because why not? We can. We have the opcode space for it. It sounds like a kind of fun thing to do. It's a bit of a joke. But it turns out there are an increasing number of legitimate use cases for having extremely large flat address spaces. Data centers are approaching the point where there are more bits of storage in the data center that can be addressed with a 64-bit number. We're not there yet, or at least not publicly announced that we're anywhere near there yet. But who knows what the NSA is doing? And also, there are lots of security applications where you might want to be able to use the extra address bits for other purposes. So I think RV128 is not a joke. It's not frozen yet, so I wouldn't go off and implement it from the spec. But I think that we will see legitimate use cases of that in not too long. All right, so that's it for the base ISAs. In my remaining 12 minutes, I am going to go through the standard extensions. So you might have noticed when I was going through RV32I that there was no multiplication and division. And the reason for that is that for some very low-end implementations, particularly those that just don't need those operations, they don't want to provide them. And the reason why is they are, in the case of divide, somewhat more complex to implement. In the case of multiply, potentially somewhat more expensive than you might want to implement. Obviously, you can implement these pretty cheaply if you want to, but for some people, even that minimal cost is too great. Furthermore, for academic implementations, say you're trying to teach this in a lower division undergrad course, they don't really help with the understanding of the ISA, and they serve to clutter the implementation because the division in particular effectively requires multi-cycle operations. So we factored these out into an extension. It's a very simple extension. It adds 8 instructions, as Rick mentioned earlier. There's the obvious multiply instruction, which just takes RS1 and RS2, forms a product, and writes it back to RD. But of course, if you multiply two 32-bit numbers, you get a 64-bit product. And in a lot of cases, you want to have access to that product. So there's 3 more instructions: multiply high unsigned, and multiply high signed unsigned, which treat RS1 and RS2 as appropriately signed numbers, multiply them together, and then take the upper 32 bits of that product and write it back to RD. So if you want the full 64-bit product, you use 2 instructions, mul and one of the 3 multiply highs. I should add, one reason this is particularly useful is it helps implement a strength reduction operation for division. So if you say divide by 3, for example, the compiler can transform that into a multiply by the reciprocal, but only if you have these multiply high instructions. So that's actually, in regular C code, that's the most common place they show up. So there's also 4 division instructions, the kind of obvious ones. There's divide and remainder, and then there's the unsigned variants of the 2. So in the base IM extension, we don't have any facility to do something like divide a 64-bit number by a 32-bit number. You have to synthesize that with software if you want it. So that's it for the IM extension. I'm going to talk a bit more. I'm going to talk about atomics now. So this A extension provides the ability to do multiprocessor synchronization. I guess I kind of lied to you. You actually can do multiprocessor synchronization without having special support for it. I think Decker proved this eons ago. But the problem is that all of those synchronization mechanisms that only use regular loads and stores, they don't scale very well, and they're inherently blocking. And so you can't implement weight-free algorithms with them. So you want some extra hardware support to do that. So RISC-V provides 2 classes of these. One of them is load reserve store conditional, which is kind of the classic RISC provide primitives, not solutions approach to the problem. And the other is pure atomic fetch and whatever instructions. I'll talk a bit more about the justification for providing both in a bit. So load reserved and store conditional, what they do is they split an atomic read modify write operation into its constituent parts. There's a load, and then there's an operation, and then there's a store. Now, because those things, the execution of those instructions is itself inherently not atomic, the store conditional operation can fail. So when you do the load, you attempt to acquire a lock on that memory address, notionally speaking. And then the store will fail if the lock is not still held at that time. And that would happen, for example, if another processor went to go access that memory address in the meantime. So what you do is you put these instructions inside of a loop. So here's an example of the use of load reserve store conditional. This one is ripped right out of the Linux kernel. They want this operation where they want to decrement a variable in memory, but only if it is not currently 0. So the way this works with load reserve store conditional is you do the load reserved. The branch there is doing the if it's not 0 part. Then you do the decrement, and then you do the store conditional of the new value. Now you'll see that unlike store instructions, the store conditional has this destination operand T1. So that's there so it can write a successor failure flag so that software can decide what to do. So the way store conditional destination is specified is if it writes 0, that means it succeeded. If it writes some non-zero value, that means that it failed. So then you just put a branch not equal to 0 instruction to retry this until it eventually succeeds. Now, you might be wondering how you don't get into deadlock situations with this, and the short answer is that the ISA guarantees freedom from load reserve store conditional live lock if you follow a certain set of relatively baroque constraints that the ISA manual lists out. Like, for example, you can't have system calls in the middle of your load reserve store conditional sequence. Kind of obvious, but you have to spec that. So in addition to load reserve store conditional, there's also these atomic fetch and op instructions, as I mentioned. And the reason we have these, I should say quite clearly, these are not strictly speaking necessary. You could implement all of these operations using the load reserve store conditional primitives. Load reserve store conditional are universal in a certain sense, at least as far as single word atomicity goes. The reason you have these is that load reserve store conditional is not a very scalable approach. You're effectively acquiring mutual exclusion on a memory address. And in a lot of implementations, what that means is you acquire a cache line in the exclusive state, and you hold that line exclusive until the store conditional succeeds. And that's fine, but that means you're sloshing around cache lines, and that's not a very efficient way to say you have a 64-byte line. It's not a very efficient way to communicate a 4-byte atomic operation. So these AMO operations can be sent to where the data is rather than pulling the data to the processor that wants to perform the operation, which for the case of highly contended shared variables is potentially much more efficient. There's also a more subtle reason why we provide them. They're useful for I/O. So if you want to do something like, say, toggle a GPIO pin, you can use an AMO XOR instruction on that GPIO register. So some other platforms have gone to lengths to provide that same facility without using AMOs. It's just kind of ugly. This works pretty well. So one other detail about the load, reserve, store conditional and AMO instructions is that they also provide a memory ordering option. They have these acquire and release bits on them, which implement, roughly speaking, the C++ concepts of acquire and release. I'm not going to go into exactly how they differ and what they mean. Dan will do that later this afternoon. But one thing I will point out is that you can optionally not have any memory ordering constraints on them at all, which is useful if you're doing things like associative reduction operations. All the processors can just hammer a variable with AMO whatever to do the reduction, and they don't have to be slowed down by memory ordering constraints. All right, so that's it for atomics. I'll talk briefly about floating point. This is without a doubt the least interesting part of the talk because the RISC-V floating point extensions are just a direct implementation of what the IEEE 754 spec mandates. So the floating point instructions add some more architectural state. They add 32 F registers. These F registers are sized to be whatever the width of the floating point type the extension specifies is. So they're 32 bits wide for F, 64-bit wide for D. Some other ISAs did things where they required you to use pairs of registers to support double. We don't do that. It's ugly to implement, and it reduces the number of named registers you have, which hurts register blocking for linear algebra operations. There's also this floating point control and status register down here, which holds the rounding mode and the accrued exception flags. So since we had any registers, obviously we added some new loads and stores. We provide the usual suspects of arithmetic operations, the 4 functions, square root, min and max. Min and max are there because they're faster than doing branching to compute those. There's also fuse, multiply, add instructions which require a new instruction format. They perform A times B plus C, plus or minus the signs there. So these take up a bunch of opcode space, but they're really important. They make it easier to build higher performance linear algebra machines, and they're also essential for implementing some algorithms because there's no intermediate rounding, so they produce a more precise result than doing those 2 operations in 2 steps. So finally, one unusual aspect of the RISC-V floating point extensions is that they have these sign injection instructions. So what these do is, from one floating point number, they take the exponent and mantissa. From the other floating point number, they take the sign, and they form a new floating point number from that. So this is really useful for the hand coding of library routines, like the transcendental functions use this. But they're also used for synthesizing more obvious operations. Like if you use sign inject, but you say RS1 and RS2 are the same, then that's how you synthesize a move operation to copy a register to another. Sign inject negative can be used to negate a number, and sign inject x can be used to multiply the signs, which, if you think about doing that for a single number, gives you the absolute value operation. There's also some comparison operations, some conversions between floats and conversions to integers. The conversions to integer actually write the integer registers directly, which saves instructions in the common case, and also simplifies the some more complex floating point unit designs where you want to have a special recoded format of the floating point number. Having integers in there kind of screws that up. One other note about the floating point ISA, we never take traps on IEEE exceptions, and that makes it easier to implement in-order, long latency floating point operations. Out-of-order implementations don't care about this detail. They can handle it just fine, but this is good for in-order implementations. All right, so I'm going to talk briefly about one last ISA extension. The compressed ISA extension is there to cope with the fact that although the base RISC-V ISA encoding is nice, it's elegant, it's very regular, 32-bit RISC ISAs just don't produce very good code density. So as one example here, the 3 most popular instructions in the GNU C library, I'm not saying this is a good corpus, it's just what I had on hand at the time, are this JAL-R instruction, which does subroutine returns, and then 2 instructions which are moving stuff around in the integer registers, like loading constants or moving registers. And if you look at the encoding of them, you see that 14 of the 24 nibbles in those instructions are zeros, which, while not really proving anything, strongly suggests the instruction encoding is not very dense. And so we want to be able to represent the most popular 32-bit instructions with 16-bit instructions instead. My timer stopped. I guess that means I get free time. some observations that help us determine what instructions to put in there are a few observations, like most instructions access a relatively small number of the registers. I think looking at spec CPU 2006, again, say what you will about the corpus, but it's just some code. 2/3 of register references go to only 1/4 of the registers. Most instructions are destructive, like the destination is equal to one of the sources. Most immediates are not very big, like they fit in about 5 bits, and only a few opcodes are very popular. So believe it or not, the add immediate instruction, the load word instruction, and the store word instruction collectively account for half of the static instructions in spec CPU 2006. So that's a useful observation for indicating what you should be trying to compress. So I'll just briefly give a highlight of the kinds of things we're doing here. There's a bunch of variants of the add immediate instruction for its idiomatic forms, like incrementing a register, loading a constant into a register, incrementing the stack pointer, generating a stack pointer relative address. There's register addition. There's register move, of course. There's the usual suspects of shifts and the other arithmetic operations. Since the other arithmetic operations are less common than add, we give them a more restricted form. They're actually only allowed to use registers 8 through 15, which are chosen to be registers that are most popular in the ABI because they're used for argument passing. So we also compress loads and stores. The most common, well, statically, some of the most common loads and stores are to the stack, for marshalling arguments and spilling and filling quality saved registers. There's also some variants that don't need to go to the stack. Then, of course, there's some control flow operations. The most common branches by far are tests against 0, so we provide those. We also provide the ability to do indirect, table jumps, function returns, stuff like that, and the ability to do direct jumps as long as you constrain the offset to be within about a kilobyte instead of in about a megabyte, is the case for the base instruction. So I'll quickly highlight one thing that is not in the C extension. This is still a matter of contention, that we don't provide load multiple, store multiple instructions. I was kind of making fun of ARMv7 at the very beginning of this talk, but the fact of the matter is that those really do help with code density. The problem is they add a lot of complexity, and that's the reason we choose not to provide them. So for example, this is just some simple C function. This is the code you generate in RISC-V for it. And if we hypothetically had load multiple, store multiple with auto increment addressing modes, you get this thing on the left. It's a lot more compact, but still the complexity led us to not include it. The other thing that led us to not include it is that we can kind of get the same effect by using software. So we can replace those load multiple, store multiple instructions with calls to these millicode routines. So effectively, we can share the prologues and epilogues between functions that save the same number of registers. So we get the majority of the savings. Of course, the dynamic instruction count is higher, but sometimes when code size is paramount, that's okay. And the effect of all this stuff is that, at least on spec, C is pretty dense. I realize this is only one corpus. And this, by the way, this is including the optimization about factoring out the common prologues, which is worth about 4%. So I think on the ARM thumb is great. It's very dense ISA. But for whatever reason, ARM dumped, well, I know what the reason is. They don't care for the implementation complexity and big superscalar processors for providing variable length instructions. But they dumped that in ARMv8, and so ARMv8 is now not a very dense ISA compared to RV64C. And you can see this by the fact that now they're using much larger instruction caches in their IP offerings than they were back when they were doing ARMv7.